Okay. Anything else? All right, when we last met, I had you do these two problems. I'm not going to do these with you, but I do want to give you the answers. You may already, in fact, I feel confident these answers are already on Blackboard. But I want to go ahead and put the answers here. That way you can check yourself. This was 1.31 grams per liter. This one would be 5,100 liters, or 5.1 times 10 to the third liters. If we have time, we'll come back and look at those. I will comment on this one. This is the one that I have had a couple students ask me about yesterday. What is the given for this problem? 30 days. 30 days is the given. Why is 30 days the given? Because this is the conversion factor. Do you see how it says 22.5 gallons in 12 hours? Conversion factors will have words such as contains, NA, per, equal to. Those are all the kinds of words that you will see, and that is a conversion factor. Once you know that, you should see time is here. There's a time there. So you're going to start with this, convert to hours to use this, and then should be able to see what to do from there. Specific gravity is the last thing on this section, and specific gravity is the ratio of the density of a substance to the density of another substance. That other substance is usually water, which makes specific gravity really simple for us, because what is the density of water? 1 gram per milliliter. So if you know the density of a substance, and specific gravity is the density of that substance as a ratio to water's density, then that means specific gravity is the same as what? Density with no units. Don't make this hard. In a question that it asks for the specific gravity, if you have the information to get density, then what are you going to do? Get density, and then what? Take off the units. That's it. It's simply no units, but same as density. Where will you see specific gravity? Anybody know where specific gravity is used in medicine? Nobody knows? Urine testing, that's the only place I know. Now, they may do specific gravity of blood. I don't know that. But I do know that at times it's used for urine testing. Why don't they just call it density? I don't know. It would make sense to me, but I don't know why they don't. So, but it is specific gravity. That's the only place I know of it being used. All right, so let's talk about energy. Some of you, by this point in the week, you're tired. And even though it's just Tuesday, right? It's Tuesday at 3:30 and you're tired. And I understand. But energy, and we're going to talk about a little bit about energy. I want you to be thinking as we're doing these problems, because energy is kind of our main focus today. But energy is the capacity to do work. So even though you may not feel like you have any energy right now, do you have any? Yes, you all have energy. So let's have a little energy to finish up some of these problems. These problems are the same types of problems that we've been doing, except all of these problems have something to do with medical field. All of these problems will have something to do with the medical field. They're no different dimensional analysis, but they have something to do with the medical field. So tell me what I would call this kind of problem. What would I say this problem is? What type of dimensional analysis problem is that one? Take a guess. Come on. Double unit conversion problem. I would call this one a double unit conversion problem because it's the only number given to me, and what does it have? 2 units. So I will set this up as 186 milligrams over 1 deciliter. And the same thing for B. What's the given for B? 186 milligrams per 1 deciliter. I promise you he can't hear you, okay? So you can talk. I promise you he will not be able to hear you. All right? So tell me now, what are the units we're trying to find? Per. Okay, look. Is that the same already? Yeah. So all you're doing is doing basically a metric conversion. That's it. I'm not going to do it. You can do that one. Come to this one. What are you trying to find? Milligrams per liter. What do we have? Milligrams. So all you're doing is trying to find deciliter to liter. That's it. So these honestly are super simple if you pay attention. So I'm going to let you do those later. Come down to the banana problem. Most of you will agree that bananas are a good source of potassium, yes? But if you were depending upon bananas to be your sole source of potassium in a day, you'll be maybe a little surprised at how many bananas you have to eat. It's quite a few bananas. So what do you think the given is going to be in this problem, and what's the conversion factor? $451 milligrams is what? Not the given. What is it? Tell me what it's the conversion factor with. One banana. Read that sentence. A medium banana, what? Contains. Is that the same thing as is in or equal to? Contains, that's the word that will trigger, hey, that is a conversion factor. So 451 milligrams equals one banana. So now what you're given? 3.5 grams. This is also a symbol and element question. Why? Because if somebody didn't know their symbols and elements and they read that, like, what's K? What is K? Potassium. So that's potassium. So there's your starting point. This is it's not more than 10, but it's more than 1 or 2 bananas a day, okay? So it's a bigger number than maybe you would want to eat in a day for getting all your potassium. All right, go to the next one. In this problem, what is the conversion factor, or what are the conversion factors? You could say one bottle is $10. You could say one bottle equals $10. What else can you say? One bottle equals 300 milliliters, and I'm not 100% sure, but I think I heard $10 equals 300 milliliters. Are those all possible conversion factors, depending upon what you need to find? Does that make sense? Something that I have been noticing when I help students, it helps if you will write down your conversion factor choices. If you will write those down, then when you get over here to start the problem, what's the given? 20 milliliters. What are you trying to find? Cost. So what do you want in the end of this problem? Unit of money, yes? You want money. You want money at the end of this problem. Do you have a conversion factor over here that you obtain from the problem that gives you money and milliliters? Then plug it in. What goes on top? $10. What goes on bottom? 300 milliliters. So what's your answer? 67 cents. So each dose costs 67 cents. The next problem is very similar to that problem, except it has an additional step. I'm going to let you do that one on your own. All right, let's go down to the 180-pound patient. The 180-pound patient is prescribed 20 milligrams of drug. What are you wanting to find in the end of this problem? What are you trying to find in the end for this problem? Give me the units. Tell me exactly the units. What are we trying to find? Milligrams per kilogram. Now, what's the milligrams of? Drug. Milligrams of drug per kilogram of what? Body weight. What kind of problem is this? What would I call it? A double unit conversion problem. It's a double unit conversion problem. So what is my given then? You have to pay attention on this problem a little closer than some others because everything's mass. So you have to pay attention to mass of what? Mass of what? What goes on top? Tell me exactly what goes on top. 20 milligrams. Because what is 20 milligrams? This is the drug. 20 milligrams goes on top. So 20 milligrams goes on top. What goes on bottom? 180 pounds. Guys, some of you are not even writing anything down. That's really bothersome whenever you're sitting and just watching. It's going to be kind of hard to study. So tell me, what's going on? What do I do here? What are we trying to find? Is it a true double unit conversion problem? Not really, is it? Why not? What do you have? You have milligrams. You have milligrams right here. There's milligrams. So all you really are doing is converting what? Pounds to kilograms. So do it. Use the conversions that you know and convert pounds to kilograms. What did you put on top? What'd you put? 1 pound? What did you put on bottom? 454 grams. Okay, some of you are using the 2.2. That's fine. If you know that one, if you have it memorized, that's fine. I don't have that one memorized. I'm not going to use that one. But you can. You can use that. That's fine. If I'm going my way, what am I going to put on top here? 10 to the third grams goes on top, and what goes on bottom? 1 kilogram goes on bottom. So there are my units of kilograms. Run your numbers. What do you get? What'd you get? 0.24 milligrams per kilogram. Anyone else get that? Okay. Did we get the same answer if you use the 2.2? Good. All right, the last question. I want you to find the conversion factors and then the given. Look through the problem, find the conversion factors, and find the given. What's the given? £183 is the given, correct. 183 pounds is the given. We're going to add some digits to make this significant figure better. Call this 2.0 micrograms per kilogram. That's a conversion factor. Call this 1.0 milligrams per 10 decimal milliliters. Now, pay attention to who's who, because you have the mass of the person and you have the mass of the drug. It's similar to this problem, but a little more detailed. Try it. Try this problem. What's the next step? Tell me what this is. What is 183 pounds? I know it's the given. What is it, though? It's the body weight. This is the body weight. So this is the body weight. So we'll call this the body. This is the body. What is this 2.0 micrograms? Say it one more time. What is 2.0 micrograms? That's drug. That is drug mass. And what's the kilogram here? Body weight. So this is the amount of drug per 1 kilogram of body weight. What does that tell you our pounds have to be converted to? Kilograms. Haven't we just done that in the problem above? Then do it again. Let me say that again. This is the body weight. The patient has a body mass of 183 pounds. They need 2 micrograms of drug per every kilogram of body weight. So you must get their mass into kilograms. It's right here how to do it. So follow suit. What goes at the bottom? 1 pound. What goes at top? 454 grams. Pounds cancel. Now you're in grams. Now what? 10 to the 3rd grams. What goes on top? 1 kilogram. Again, let's comment on what we're doing. This is the body weight. This is simply converting body to kilograms. The body weight to kilograms. That's all that process is doing. Once you are in kilograms, what are you ready to do now? Figure out what? What conversion factor can we use? Say it, 2 micrograms. 2 micrograms per 1 kilogram. Kilograms cancel. This is drug, this is body. Once we get to this point, are we just in drug? Are we in drug only here? Yes, we're in drug mass right now. We're out of body mass. We are now in drug mass. What's the question asking for, though? It's not asking for micrograms of drug. It wants to know milliliters of drug. So if it wants to know milliliters of drug, then what do we know about milliliters of drug? There is 1 milligram. That's okay. There's 1 milligram per 10 milliliters. Will this be the last step? What are we trying to find in the end? So am I going to use this conversion factor at the end? Yes, but I'm not ready for it yet. Why not? What am I in? What do I have to be in to use this conversion factor? So what's my next step? Micrograms to milligrams. So do it. Figure out micrograms to milligrams. Micrograms to milligrams. What's the conversion from micro to milli? Who's bigger? Milligrams is bigger, so where's milligrams going to go? On top, so 1 milligram on top. What goes on the bottom? 10 to the micrograms. Good. So micrograms cancel, and then my last step. What goes on top? 10 milliliters per what? 1 milligram. So again, this is drug mass. This is drug volume. And you're done. So run your numbers. Do you get 1.66164 on your calculator? Yes. All right. Significant figures, how many? 3. This is 3. Come on. 3. Doesn't count. 2. I made it 2. I fixed it for 2. This doesn't count, and these are each 2. So what's my final answer? 1.7 milliliters. Good. Question. I'm not sure how some of you are studying. Earlier, last week, you guys seemed to be just really, really on it. Today, I'm not sure if it's the video or what, but I'm a little concerned today, just based on what I'm seeing and hearing. When you study, I would strongly encourage you to talk these problems out to yourself. I won't go through this one because I just did this. But let's say that you're going through your notes. Here's what I hear people tell me. After the first exam and they bomb it, they come back to me and they say, well, I studied. I don't know why I failed that test. I studied. Well, what did you do to study? Well, I looked at my notes Well, looking at your notes is a big difference than studying your notes. So I want to give you an idea to try. I'm just going to go back to this problem. Now, you may think that I'm being silly to do this, but I want to tell you why I'm going to do this. Many people are auditory learners. However, you don't learn by hearing me speak. You learn by hearing yourself speak. You teach yourself. Hearing me is just a bunch of garbage a lot of times for some of you. Hearing yourself will teach you. So when you study these notes, without anybody else around, without any distractions, no cell phones, nothing on, this is what you should be doing. Literally what I'm going to do right here, this is what you should be doing. Okay, what is the mass? Okay, she wants to know mass. So she wants to know mass, and we want it in pounds. And the volume is this many cups. So, volume and mass, I'm going to have density because that's the only thing that gets you from a mass to a volume. Yeah, because density is mass to volume conversion factor. All right, so I start with volume. That's volume. So I start with volume, and it's in cups. She gave us density, and it's in grams per milliliter. That's volume, isn't it? And that's mass. So I'm going to have to somehow get cups to milliliters. Well, I remember, oh yeah, she put, so that's right, 2 cups in 1 pint. Yeah, I remember because it had quarts and milliliters. So I do 2 cups in 1 pint, 2 pints in 1 quart. 1 quart is 946 milliliters. Why did she do that? Oh, because that's milliliters, and we got to get that to cancel. Okay, so yeah, do you see what I'm doing? Now that sounds real corny for me to sit there and talk about it like that to myself. But that's what you need to be doing. Many of you need to be doing that. Sitting here and saying, I don't have a clue what she did. That's what some of you are going to do. I need to go to PASS because I don't have a clue what she did. And you're sitting in class not paying attention. PASS isn't going to solve your problems. You need to sit down and do that, okay? You've got to do that. You've got to sit down and talk to yourself. Some of you more than others, okay? May not be hitting home today. It may later. I want you to do well. You've got every avenue to do well. You've just got to put a little effort in, okay? So let's go back now and let's deal with energy. So we all know that you have energy whether you feel like it or not. You've got energy. Energy is the capacity to do work or the ability to do work. What is the go ahead. Always multiply the top, always divide by the bottom. Always. I go in the order that they're in on the paper. That's how I go. If you didn't get the answer on the last one, see me after class and we'll look at it. Okay? All right, so when we're looking at energy, energy is the ability to do work. And even when you don't feel like you have energy, you have energy. Even when you are sitting still, you have energy. Tell me some of the forms of energy that are going on in your body.
Breathing.
You're breathing? Your heart is pumping? Digestion? Say it again. Your whole body's working, isn't it? Inside, there's still a lot of activity. Y'all seen that movie Inside Out? I mean, you can kind of imagine what's going on inside, right? So you've got all this activity going on inside of your body right now. All of that energy originated from one source. Anybody know what source it all came from? The sun. The sun is the source of energy for the earth. That is the source of energy for the earth, is the sun. Now, I'm not going to go through all the different forms of energy that the sun, we're going to talk about that, but I'm not going to go through all the different forms. But there is a law called the law of conservation of energy, and it says that energy is not what? Created or destroyed, it changes from one form to another. Energy is not created or destroyed. It changes from one form to another. Now, I am not a physics teacher. If you had a physics class, you would have a lot more details than I'm going to give you today. But that is our short and simple definition of energy. So we're going to deal with two forms of energy first. We're going to deal with potential and kinetic. Potential is what? Energy that's stored energy. Or sometimes we say energy due to position. Kinetic energy is energy what? Due to motion. Right now, you have both. You have potential and you have kinetic. You are moving inside and outside, and you have potential energy. The food that we eat would be what? So a baked potato. What would a baked potato be? What form of energy would that be? Potential energy. That would be potential energy for us. What is water behind a dam? Potential energy. Then as it's flowing over the dam, the potential is converted to kinetic. And is there going to be some sound energy when it falls? Have you ever heard a waterfall? We went to Cumberland Falls before school started. And Cumberland Falls, you could hear the roar of Cumberland Falls before you got anywhere near it. You couldn't see it, but you could hear it, because that's a massive amount of water coming over those falls. And then you hear that noise. And so the potential energy, and it's kinetic too, coming down the Cumberland River, it's the potential and kinetic. Then it gets to the point it's going to increase its kinetic energy as the potential's decreasing, because as it gets closer to the bottom of the falls. And then it's going to have the sound energy, and it's just going to continue. Now, are we getting light when Cumberland Falls, when that falls over the falls? Are we getting light? No. But is light a form of energy? So there's a lot of different forms of energy. We know that energy is transferred from one form to another. And you've already told me that the energy source is the sun. So if the sun is the energy source, explain to me, just give me a quick synopsis, just to make sure we all remember this from elementary school. Give me a quick synopsis of how that cycle works. So the sun gives us what? Gives us a lot of things, but what are some obvious things? Heat and light. It gives us heat and light. What's today compared to last week? Cooler, isn't it? What's not shining much today? Sun's not shining much today, or yesterday did it? It's cooler today than it was last week when the sun was shining. There's other factors involved, but that is definitely a factor. When the sun, I mean, even today when the sun came out a little bit, you could feel the warmth just a little bit compared to what it was when it's not out. We get the light from the sun. Those are forms of energy. What does the sun shine on? Us. What else? The grass, the plants. Do we eat the plants? Do we get energy from the plants? Yes. So we get energy from the plants. All right. Tell me what else gets energy from the plants. Animals get energy from the plants. Now, you may be a vegetarian. Forgive me if you are. But do we eat the animals? Some of us eat the animals. So what do you eat that grazes in a field? Cows. I always love this lecture because I want to hear you say that. Because here's my goofy question. I have to teach you a little ag here, okay? So is it a cow that you eat? Do you think you really eat a cow? Do you know what a cow is? Tell me more specifically. You're right. The cow is the female that has what? Has had a calf. Good. The cow is a female that has had a calf. Do we think about that now? Chances are, do we eat a lot of cows? No, we actually don't eat a lot of cows. Now, some of you have been called what you might have thought was a very rude name that's a bovine name. Do you know what bovine means? Bovine means cattle. That's bovine. So when you say that the cows are in the field, really you're probably saying bovine are in the field. We don't normally say that, though. All right, so you have been called, some of you girls have been called a heifer. Have any of you been called a heifer before? Have you been called that before? The funny thing is you probably don't know what a heifer is. What's a heifer? Say it again. Not pregnant necessarily. A heifer is a female that has not had a baby yet. So the reason that they give heifers the bad rap is because heifers are usually much more flighty than cows are. So like in my herd, the heifers are going to be the ones that are harder to deal with. After they have their first calf, they seem to calm down a little bit. But a heifer is usually more flighty. She won't pay attention to you. Then after they have their first calf, they seem to calm down. So the cow has had a calf. The heifer has not had a calf. So that's a young female. A heifer is a young female who hasn't had a calf. Now, we don't eat heifers usually either. Now, sometimes we do, but not always. Probably eat more heifers than we do cows. We normally eat what then? Do you know the word of what we normally eat? Steer. Somebody knows from agriculture. Good. We normally eat steers. Now, does anybody know what a steer is? It's a male that has been castrated. We don't eat the bulls. Bulls are intact males. We typically don't eat bulls because they have a foul taste. We typically eat the steers that have been castrated. So let's go back to our sun now. So we go back to the sun. You had to have that little ag lesson. So we go back to the sun. The sun shines down. And out in the field, now we're going to be more specific. Out in the field, we have a bunch of steers that we're going to eat. And so the steers are out in the field, and I have the steer killed, and I'm eating a steak, and okay, so let's go back before I stop there. So tell me about the energy. The energy from the sun has been shining down on the grass. Tell me what process that's called. Photosynthesis. So photosynthesis, I'm trying to wake her up. Wake up. Photosynthesis. So there's photosynthesis that's doing what with the grass? Giving it energy, isn't it? And what's that making for us then? Carbohydrates? If we eat the grass, we don't eat the grass. But the cow gets the carbohydrates and the energy from the grass because of that photosynthetic process. So I then kill the cow, or the steer, eat the steer, have the steak, and I choke to death and die. Okay? So what I want to know is, do I no longer have energy? Did I stop the energy cycle? No. Why not? Put your phone up. All the way. Do I stop the energy cycle? No. Why not, though? What am I? Somebody said really funny, and you can say it. Somebody said, because you're worm food. That's what they told me the other day, and that's true. That's what happens. So I didn't just stop the energy cycle. Now I am what? Potential energy. So do I then get eaten? Now, here's the thing that's funny, though. Not funny. I'm not trying to be morbid, okay? But it is kind of funny. What do they do when here in the United States when someone dies? We embalm them, which is a preservative. And then we put them in a casket, then we put them in a concrete vault, then we put them 6 feet under. It's really hard for the worms to get to you. So does that mean we stop the energy cycle? No. No. Because am I still potential energy? Yes. I haven't reached my full potential yet, but I am still potential energy. Isn't that interesting, though, when you think about that? So cremation, you'd reach your potential quickly then, because you're immediately giving off heat. I'm not promoting that. I'm just giving you the details, okay? The whole point, though, is all that, again, went from one form to another. Like before I died of the steak, what was I using that energy for? Movement, heart rate, whatever, brain activity. So the point is one form is converted to another. So you get that one. That's pretty straightforward. Now, what about the lights in this room? How do the lights in this room have anything to do with the sun? Somebody knows this. Excuse me? True, the sun gives off light, but this, I'm saying, how does this relate in that one form to another form? How in the world did this light come from the sun? Say that again? But how did it come from the sun? How can I say this energy that this light is giving off came from the sun? If all energy comes from the sun, how did this light come from the sun? What do you think? Say it again? Yeah, but where did it come from? What stored energy eventually got to this? You guys should know this. It is an electrical current, but how does that electrical current get made? Ryan, tell them. Coal. Coal and natural gas. This is always where I get scared when I teach this class. And you guys are like our future leaders. This scares me. Okay? You should know this. How is our electricity made? Much of it is from coal-fired power plants or natural gas-fired power plants. Do you know this? Now you do. Okay. What do coal and natural gas have to do with the sun? How were they formed? What are they called? Coal and natural gas, petroleum are called what? Fossil fuels. Plants, animals, whatever, died a long time ago, and they got buried, and then over years and years and years and years of pressure, temperature changes, all of those good things happened, and what did we form then, or what was formed? Coal, natural gas, petroleum, those fossil fuels. So did the sun give energy to those things? Yes. So that is now coal, natural gas, petroleum, which in the power plant is burned. Coal and natural gas are burned in the power plant. They are burned to do what? How? I want to know the how. I want to know what you know. How are they burned? What's the purpose of burning coal and natural gas? Burning coal and natural gas? Oh, yeah, man, I see the coal from right there. No. Yeah, it's black. It's a black light. That's how black lights are formed. It's coal burning. Did you know that? No. How? Heats water. What's that water turn to? Steam. What's the steam turn? Somebody saying it? Turbine. The steam turns a turbine. The turbine then turns a generator, which then produces electricity. Some of you probably live near a power plant. You need to know how that works. All of you, whether you live near one or not, need to know how that works. So when you hear all about coal in Kentucky, coal keeps the lights on, you've seen those license plates, why are people saying that? Why are there other people who hate coal? What's all the fuss about? That's part of it. This probably came originally from coal, which came from sun. Now, what are other sources that would be more direct? Now, obviously, when you think about coal and natural gas, they are having to be burned to heat the water, to convert it to steam, to turn the turbine. What would be a more direct approach? So, forget solar for just a minute. Wind or what? Water. A waterfall that turns the turbine directly, or wind? Why don't we all have windmills in our yard? Why don't we all produce our own electricity in our own yard with a windmill? Well, they're not just loud. They are loud, but we don't have enough wind consistently. We might have electricity one day and wouldn't have the next, because we in Kentucky don't have consistent wind. So that would be a problem. Do you live near a wind?
I live in Chicago. On the way home, there's a windmill of like 800 windmills.
And you've seen it, and you hear the noise, you can hear the roar?
We have it in my neighborhood too.
Yeah, so you've seen, and so you are in the Windy City. You've got more wind than we have, so you're going to have windmill power. We don't have that. Solar power is definitely direct, and nothing has to burn, and that's just a conversion of photovoltaic energy to the AC/DC current that we have. That's what you're seeing there, and that's probably not the right electrical term, but it's a conversion like that. All right, so tell me, what about the, so we've got the coal, we know the natural gas, so now then let's go back to us about energy. We use energy. What do we do to get energy? Eat. We eat food to get energy. What is the number one use of energy in your body? Not brain. Not breathing. What'd you say? Keep us warm. What are you all wearing, some of you today, that you weren't wearing last week? Sweatshirts and pants. What are you trying to do? Stay warm. Are you trying to conserve your energy? Now, if you know someone who is anorexic or bulimic or doesn't eat enough, what are they always? Cold. Why are they cold? Because they have to have enough energy to keep them warm. We use the majority of our energy to keep us warm. We have to take in enough food to keep us warm. Now, another freebie for you today. Newborn babies. Some of you may work in a NICU. Some of you may become parents. Some of you may be parents. Tell me about newborn babies. What is their number one use of energy? If ours is to keep us warm, what would theirs also be? To keep them warm. So have you been to Walmart or Kroger or wherever sometime recently and seen this little bitty newborn baby in a onesie and nothing around it, and it's probably screaming its head off? Why? It's probably cold. It's probably cold. Why does the grandmother say, swallow that baby, keep that baby warm, put some booties on that baby, put a hat on that baby? Why do they say that? Do you know why they say that, really? Because where do they get their food? What's their energy source? Breast milk, we hope. If it's not breast milk, it's formula. They can't just go to the refrigerator when they're hungry. So they have to depend upon someone to give them the food they need. What do you want that food to go for? Do you want that food only to go to keeping them warm? Where do you really want most of that energy to go? Brain development and physical growth. There's a condition called failure to thrive that's very real. If a baby does not get enough food, it's not going to grow like it needs to, and its brain's not going to develop like it needs to, and it's probably going to have developmental delays. It may not roll over by the time it should, because it's spending all of its energy trying to do what? Keep warm. That's why you keep a baby wrapped up. I'm not saying, one of my kids said, put a heat lamp. No, you don't put a heat lamp on a baby. You don't wrap them in no, you don't burn them up. You don't want to fry the poor kid. But you have to keep them warm. It's very important to keep the baby warm. And if you've ever known a baby that maybe was a real just laid back baby and nobody ever really thought the baby was hungry, but it was, and later it never grew, it never gained weight, and then they go to the doctor and it's like, what's wrong? My baby is really peaceful all the time, but it's not crying because you keep whatever, it's being held all the time or something. And then they're still not gaining weight. It's because they don't know they're hungry. Then that happens. And then they're going to have delays. So it is something to consider. We wrap up. Remember, the baby might be cold too. So remember that. All right, the units for energy, you've got them there. Later, I want you to add these to your list of things you need to know. Same thing for these units. You are responsible for knowing these units. Those are conversion factors. So that's 1 small c calorie equals 4.184 joules, and 1,000 small c calories is 1 kilocalorie. or 1 big C calorie. And then you also, if you don't already know this, the protein, carbs, and fat, that's 4 big C calories per gram for protein, 4 big C calories per gram for carb, and 9 big C calories per gram for fat. Those are all exact. Make a note of that because it's not on there. All of these are exact. That means no significant figures. Now, what about this big C calorie? Anybody know anything about the big C calorie versus a little C calorie? Food calorie. Does anybody have a food container by chance today? May I borrow your Dr. Pepper? All right, what do you see there in this Dr. Pepper? 250, and what does it have there? Big C calories. 250 big C calories. So for one bottle, it has 250,000 calories. Now, whoa, she's thinking, no wonder I don't lose weight. I want to. It's all relative, though, because the little exercise machine that says you burn 200 calories, those are what? Big C calories. So those are big C calories just like these are big C calories. Now there is a mistake on this label though. And there is a mistake on every food label I have ever looked at. I've never seen this correct. Does anybody see the mistake? Do you see that down at the bottom left where it says percent daily values are based on a 2,000 small C calorie diet? That means that if you drink this, then you've just totally blown your 2,000 calorie diet because you had 250,000 small C calories for your 2,000 small C calorie diet. It's wrong. This is wrong. This is wrong. I've never seen one that's right. I would say why it is wrong is because here this is a heading, and so they capitalized the C. This C is in the middle of a sentence, and so they didn't know to capitalize it. They're just, but I've never seen one right. Ever, never, ever seen one right. It's really funny because it's wrong every time. So let's talk just to make sure you all keep eating, okay? These are based on a 2,000 big C calorie diet, and these are big C's. And when you exercise, the little machine tells you your exercise in big C calories, okay? Keep eating. Keep eating. Don't just stop eating, okay? But that's where that's coming from. Why do you think they came up with a big C calorie for nutrition? Can you imagine putting all those zeros or scientific notation on the food containers? You're not going to have that. So figure out how many calories are in a baked potato. A trace of fat simply means just a small amount of fat. And there's a trick you could do at the beginning of this one if you want to make it only one problem. What would you do to make it just one problem instead of two? What is your protein and carb? What's the similarity between protein and carb? They both have what? 4 calories per gram. So this is 4 calories per gram. This one is also 4 calories per gram. So if you simply add those together, you get 26 grams. And you could just do one problem that way. And then what's your answer? What do you get on your calculator or in your brain? 104? All right, significant figures. Tell me what counts. These are all exact, so they don't count. And what's the rule for addition? Precision. So are these precise to the ones? Is this correct as precise to the ones? Yes. So this has 2 significant digits. This doesn't count. What's my answer? Do I put 100? I can't. What do I have to write? 1.0 times 10 to the second big C calories. 1.0 times 10 to the second big C calories to have 2 significant digits. It has to be written that way. Yes?
So you wouldn't add 9 because it's just a trace of fat?
It's just a trace of fat, means negligible, not enough fat to worry about. If you, yes? You may. I mean, I can't tell you whether you will or not. Anytime you see a trace of anything, don't worry about it. Don't worry about it. All right, if you're interested in more about this, I don't know if you've heard of MyFitnessPal. Most people have by now, though. But it is a neat little app to use to keep up with what you do consume, and kind of a fun thing to look at and pay attention to. All right, the next little section deals with kind of a review about states of matter. I'm not going to spend much time on here, but I am going to relate this to energy. We didn't really deal with energy much when we talked about the 3 states, but let's go back to those and talk a little bit more about them. Which of the 3 states do you think, phones and watches are the same, which of the 3 states do you think would have the most energy? Gas. Because why? It's moving fastest. It'd be moving the fastest. Good. Then who would be next? Liquid, and then solid. Solid's going to move the slowest, okay? Now then, energy is also how the molecules interact with each other, or within the molecule, within the substance itself. Solid are going to interact very, very strongly. They have very strong interactions. That's why it stays in a certain shape. Strong interactions for a solid. A liquid would also have strong interactions. And a funny way to remember that is simply think about pouring a liquid. When you pour a liquid, what does it do? It stays together, doesn't it? I mean, that sounds corny, but just think about pouring a glass of tea. What does that tea do? It doesn't just randomly spew everywhere, does it? What does it do? It stays in a nice, like, little line. It flows together. That means they have strong interactions, and that's stronger energy. And then gases, what about gases? Gases have no interaction between particles. They're just going to go. They don't have to have each other. They just go away. Just get out of here. They don't need any interaction in themselves. And so that is also relating to energy. And then the changes that occur to make a solid change into a liquid or a liquid into a gas, that also involves energy, yes? What do you have to have in order for a solid to melt? What do you have to have in order for a liquid to freeze? That one's funny. You're going to say cold, right? Lack of heat. So we're talking about endothermic and exothermic changes that are occurring. Endothermic means, anybody know? Anybody know what exothermic means? Exothermic is releases energy, and endothermic is absorbs energy. Endothermic is absorbing energy, exothermic is releasing energy. I do want to point out that a release of energy, this may be heat, it may be light. An exothermic reaction is what you see in a glow stick. That's giving off energy. That would be an exothermic reaction. So some changes that we see are melting and freezing and boiling and condensation. So let's look at what those would be. A solid to a liquid is called melting. Think about that very closely and tell me, is that exothermic or endothermic? Solid to a liquid. What do you have to have in order for a solid to go to a liquid? So was it endo or exo? Endothermic, because it is absorbing energy. It has to absorb energy in order to melt. That is called heat of fusion. I'm not going to ask you heat of fusion again. I won't ask you that term. But that is called heat of fusion, and it's the amount of energy required to melt 1 gram of a substance. The heat of fusion has units in calories per gram. Now, how would this solid changing to a liquid being called melting, how does that relate to freezing? And it's super simple. Don't make that hard. It's the opposite. It's the opposite. So if this is the opposite of melting, what is freezing then? It's exothermic. Now that one really blows you out of the water if you're not thinking about it. But think just for a minute. In order for this liquid water to freeze, what does it have to do? It's got to do what? Release heat. It has to release its heat in order to get cold enough. That's why it's exothermic. That is why it's exothermic. All right, these two problems are both math problems. And honestly, you don't have to know anything about heat of fusion to do these problems. Why not? Look at these problems. What do you have? You have a conversion factor, you have a given. You have a given, you have a conversion factor. Solve them. Solve these two problems. And then we're going to look at the concepts. I know you can do the math. I want you to understand the concepts. So do the math, then we'll look at the concept. First one should be pretty simple. So tell me what you have for the first one. What's your given? 50 grams. Then what did you put on top? 0.7 calories per gram. Grams cancel. There's your calories. Do you get 3985? And how many significant digits should you have in your final answer? So what's the final answer? 3990. It's not just 399. It's 3,990 calories. Or you could have 3.99 times 10 to the third calories. Either one is fine. All right, the next problem. And then we're going to talk about both of them. Let's just do the math, then we're going to come back and talk about both of them. What is the given for the next problem? 3.5 pounds. Start with the given. Start with the given. Don't start with the conversion factor. Start with the given. Is this really any different than the other problem? Except what do you have to do with 3.5 pounds? Convert pounds to grams. What goes on bottom? 1 pound. What goes on top? 454 grams. What goes on top? Calories per gram. And then we want big C calories this time. So what goes on top? 1 what? Big C calorie and 1,000 small C calories. Now, somebody says, where did this come from? Where did this come from? This is the one I said you had to know. You've got to know this. This is when you need to memorize. Go ahead.
Like if we have a question like this, are you going to give us the H2O and 79?
I would give you heat of fusion, absolutely. You don't need to memorize. The only thing you need to know as far as like a conversion factor that's not on those main lists that is like density of water, you need to know that one. But other than that, for a specific substance, the density of water is it. You don't need to know any other densities. I'll give them to you. Yes, good question. All right, so if you run the numbers, do you get 126.64? All right, significant figures, this counts for how many? 2? Come on. 3, and this is exact. So my final answer should be what? 2. So what's my final answer? Here my 2. Does the 6 make a 2 go up? Yes. So what's my answer? 130. Guys, you can't change the magnitude of the number. You cannot change. If it's 100 something, you have to keep it 100 something. Don't change the magnitude. I do not doubt you can do the math, or at least I hope you can do this math. The math should not be hard. What did you do? That's what I want you to understand. What did you do in this problem? So I'm going to talk about this one first. You have 50 grams of ice. Okay? I can't tell you how many cubes of ice that would be. I don't know. But just imagine, say a handful. Okay? Say you've got a handful of ice. First of all, just common sense says, what's that ice going to do in your hand? It's going to melt. Okay? Where is it going to get the energy needed to melt? From your hand and from the air temperature. Okay? The question is, how much energy did it take for 50 grams of ice to melt? 3,990 calories. That would be almost 4 Big C calories. So, like the energy in a Tic Tac. Isn't that like 1 or 2 calories? So 2 Tic Tacs worth of energy would cause 50 grams of ice to melt. Does that make sense? So that would be the amount of energy. Now let's go to this problem. This time we're going the opposite direction. This time we have water. And what are we trying to do? Freeze our water. This is 3.5 pounds of water is a little less than a half gallon. That's a little less. So it's around 2 quarts. It's a little less than two of these jars. That would be about 3.5 pounds of water. So it tells it. The question is saying, how much energy is released if you have 3.5 pounds of water? How much is released? 130 Big C calories. So half of that Dr. Pepper bottle of energy, half of the energy that's in that Dr. Pepper bottle is released for 3.5 pounds of water to freeze. Now, folks, do the flip of that. Take 3.5 pounds of ice. How much energy is used to melt 3.5 pounds of ice? Come on, what is it? 130 Big C calories. If it releases this much, then is it going to absorb that much? Now, I have a new weight loss book coming out. It's called Eat Ice. Now think about that for a minute. I can eat 2 quarts worth of ice, 3.5 pounds of ice, and I will burn 130 calories just by eating the ice. Why? Why does that work? Because what does my body have to do? My body has to use energy to heat that ice up. And guys, do you know how hot you are? Somebody told you that lately? You're hot. I mean, you are hot. Think about how hot you are. How hot are you? 98.6 degrees Fahrenheit. You're hot. You don't know how hot you are? Pee on yourself the next time you take a shower. You will be amazed at how hot you are. I'm not joking. I said take a shower. I didn't just say go pee on yourself. But next time you're in the shower, pee on yourself, and you'll be like, whoa, I am hot. I mean, you are hot. If you don't want to pee on yourself, then go get blood and fill up your blood bag. And you will realize how hot you are. So now think about that. We use energy to do what? Keep ourselves so hot, right? We got to keep ourselves so hot. We got to use our energy to keep ourselves hot. So I'm going to use a whole lot of energy to keep this old body hot. And then I can eat ice. And that's just using more energy because all that cold, cold ice has to heat up to 98.6 degrees Fahrenheit. Do you see what's happening? So not only am I going to be selling this book about eating ice, I'm going to say eat all cold food. Because all cold food has to do what? Now, why isn't there a book written on this already? Wouldn't it work? It's not going to use that many calories, but does it burn some calories? I wouldn't advocate eating ice because you probably will have no teeth left. But slushies, ice cream, cold Snickers bars, I mean, you name it, put everything in the freezer. If you ever had frozen grapes are really good. I mean, eat everything cold and you're going to burn more calories. That's just, I'm telling you, it's the truth. I'm not joking. It really is true. I mean, I know it sounds funny, but it really is true, okay? So just remember that. All right, heat of vaporization is the amount of energy needed to vaporize 1 gram of substance. So tell me, when you convert a liquid to a gas, it's called vaporization. What is it? Endothermic or exothermic? It's endothermic. Good. Because it has to absorb energy. How does this relate to condensation? Opposite. So that means condensation is what? Exothermic. Real quick, let's talk about condensation. Take a shower. What do you see on the window or on the mirror in your bathroom? Condensation. That's what you see. So what do you see? You see the steam that has cooled down, so it's condensed. That's what you're seeing. So solve the math problem, and then let's talk about it. So solve the problem. Guys, make sure you start with your given. Don't start with the conversion factor. If you have a choice between a 1-unit number and a 2-unit number, what is the given? Which one? The 1 unit. So what is the given? 22 grams. So what's the next step? 159 calories over 1 gram. Grams cancel. We want to know what, though? What do we want to know? Kilocalories. So what goes on bottom? 1,000 small c calories, 1 kilocalorie. So run your numbers and tell me what you get. Now, significant figures, how many should you have? 3. So what does your answer have to be? 3.50 kilocalories. 3.50 kilocalories. All right, let's talk about what you just did. Math-wise, again, I hope those are not a problem math-wise, but what is this problem talking about? All of you, I imagine, at least 99% of you, have experienced this scenario. All of you have probably experienced this. Tell me, in your real world life, where you have experienced this scenario. I'm not saying that they've necessarily used 22 grams of rubbing alcohol on you, but you have experienced this phenomenon taking place. Tell me when, give me the scenario of when it happened, where it was, what was going on, what was being done to you when you get a shot. When you get a shot. So they say, pull up your sleeve, and what do they rub on your arm? Rubbing alcohol. What does it feel like? Now, let's talk about that. So here, they take 22 grams. That's a little less than 22 milliliters. Okay, remember, that's a little less than 22 of these, 22 milliliters. And so that's a lot. So let's say they just poured that on your arm or poured it on your leg. It's going to feel what? It's going to feel cold. Why? What is it getting from your body? How much? 3.50 kilocalories. Does that make sense now? Literally, energy is coming out of your body. It's being absorbed out of your body. It's getting that energy out of your body so that it can do what? Change from a liquid to a gas. That's why it feels cold. So new weight loss plan, put rubbing alcohol all over your body and eat cold food, and I guarantee it'll work. You'll lose weight. Okay? You might stink, probably have bad skin, but hey, you'll lose weight. Okay? It'll work. Okay, so last one, change is called sublimation. Converting a solid to a gas is called sublimation. This one we don't talk much about, and people really don't even think it exists, but it does, and I can prove it. First, though, we'll do the one you know about, dry ice. You know about dry ice. So if I have a hunk of dry ice up here, what do you know is going to happen? I put the dry ice in here, and I just say, you don't know I did it, but I just have it up here all of a sudden. What happens? What are you going to see? You're going to see fog. Now, here's what's interesting. Most people think they're seeing the dry ice. Dry ice is carbon dioxide. So it's solid carbon dioxide is what I would lay up here on the table. You're not seeing carbon dioxide, though. Carbon dioxide is colorless, odorless, you can't see it. What is it you are seeing? Water vapor. That's exactly right. Because what is in this room? With what in it? Water vapor. And so what's happening when you put that dry ice on the table, what is it temperature-wise compared to this room? Cold. So as it sublimes, meaning the gas is coming off of it, and really it's probably doing this, it's heavier, more dense than air. So as it's coming off of it, what do you start to see rolling on the ground? Fog. You see cold water vapor. What you see when dry ice is evaporating or subliming, it's not evaporating, it's subliming, is water vapor. That's what you see. You don't see the dry ice, the carbon dioxide. You see water vapor. Now, what's really interesting is that you have sublimation going on in your freezer right now at home. You don't realize you do, but you do. And it's not, some people say, oh, is that what happens when I open the door? No, that's the same thing that this is. That is the cold air hitting your moist air in your kitchen and it causing a cloud, a fog. That's not what I'm talking about. Go to your ice cube tray. If you have the old-fashioned trays that you fill up, then you will notice it probably more than you will if you have an automatic ice maker. But if you have an old-fashioned tray that you fill up, look at one that you just filled up 2 or 3 days ago, and you're going to have these big, nice, full, fat ice cubes. Leave it in there all semester. Or if you really want to do an experiment, fill a cup, a paper cup up, just a small one, with water about halfway. Let it freeze solid for 2 or 3 days. Go back, draw a ring inside the inner cup, inside the cup, showing the level of the ice. Wait all semester, go back and look at it at the end of the semester, and it's going to be shrunk. Now, where did it go? Did your cup leak? No, it's sublimed. If you don't believe that that happens, do that experiment, but then there's another application that you all have had maybe happen. Have you ever had something freezer burn? So let's say that you go and you buy a steak, but you can't eat it because you forgot you had a meeting, you put it in the freezer, somebody gets in there and starts digging around and they put a hole in the plastic. You come back a month later, you're going to have your steak, and you look at your package, and where that hole is discolored. And tell me about the texture of that meat right there. It's dried out. How did it get dried out? Well, what was in it? Water, moisture. So how did it dry? How did it get dry? That water was frozen, wasn't it? So what had to have happened? Sublimed. That's what freezer burn is. Freezer burn is sublimation. That's what freezer burn is. All right, last page is the graph here, the heating and cooling graph. And I'll be very honest with you. The main reason that you have this on your page is because many of you do not know how to read a graph. And I think it's very important that you know how to read a graph. So I want you to label A, B, C, D, E, and above. I want you to label this graph, and I want you to answer these questions right now. Label the graph and answer the questions. All right, does this graph represent a heating or cooling curve? Heating, good. What is the melting point? 40 degrees Celsius. Now then, even though this is not what you might consider a measuring device, it actually is a measuring device because it's the measurements for this graph. So we have to use proper significant figures. Why do I put a decimal? Because it is on the line. And as you see in the boiling point, what do you have to do? You have to make an estimate. So what's your estimate for the boiling point? 78 degrees Celsius. Maybe you put 77. Either one would be acceptable. Before you answer the next two questions, tell me, what is this phase? And gas. So now the question is, what phase or phases are present at Plateau, BC? Solid and a liquid. Solid and liquid. Now that confuses people. I want to explain that for a minute. If you are exactly, let's talk about water because you're familiar with water. If you are exactly 32 degrees Fahrenheit, you will have both solid water and liquid water. If you go to 31.5 degrees Fahrenheit, you're going to be what? All solid. If you go to 32.5 degrees Fahrenheit, you're going to be all liquid. But at that exact point, because what is the melting point called? The freezing point. What's the freezing point called? The melting point. It depends on which side you're standing on for sure what state you're going to be. But exactly that, you will be both. So at exactly the boiling point, what's going to be present? Liquid and gas. So a couple more labels you could put here. We could call this the melting or freezing point. And this is the boiling point. All right, the last two questions are good compilation questions for dimensional analysis as well as energy. I'm not going to do the first one, but I'm going to get you started on the first one. Read that and tell me what do you have to do first before you can really do dimensional analysis. And it is partly dimensional analysis, but what do you have to figure out first? How many calories are in the cheeseburger? So make a note to yourself. First, calculate calories in the burger. That's what you need to do first. You've got to calculate the calories in the burger. And then after that, you should be able to figure out the rest of the problem fairly easily. The last one is a very good compilation problem. I want you to look at this one, pull up any of your other practice problems, and try it. Figure out your conversion factors, and then figure out what your given will be. What do you start with? What's the given? 1.0 gallon is the given. So 1.0 gallon is the given. Let me ask this question. What is the final answer going to be in units of? What kind of unit is that? Energy. What's the only conversion factor that gives you anything about energy? Kilocalories per gram. This is energy, right? So is this going to be used toward the end? Yes. But notice what it's with. Grams. This is what? Which is volume. What is the only way to get a volume to a mass? Do you have density given to you? Yes. So then that tells you what do you have to get gallons to be able to use this? You've got to be able to get them into milliliters. We've done that more than once. What are you going to do? Gallons to what? quarts. So what goes on bottom? 1 gallon. What goes on top? It will be. Absolutely. Think about what gasoline moves. A car. You tried pushing a car? Takes a lot of energy. So now what? Quarts to what? Tell me what that conversion factor is. 946 milliliters is what? 1 quart. Quarts cancel. That's right. Say it again. Now you're ready for density. Now you're ready. So 0.74 grams, 1 milliliter. Milliliters cancel. Do we have grams somewhere listed in a conversion factor? Yes. So what goes on top? 11.5 kilocalories. And what goes on bottom? 1 gram. Grams cancel. That one came from there, if you're wondering. And then what do we have? 1 kilocalorie is what? 1,000 calories. And what is the joule to calorie conversion? 4.184 joules per 1 calorie. So run your numbers. Very good. Somebody knows how to read numbers well. Most people won't say what that number is. Good job. How many significant digits? 2. Why? How many do you have here? 2. What about this? Does not count. 3. 2. 3. Doesn't count. Doesn't count. So we need 2. How do you write that with 2 significant digits? What I would do is 1.3 times 10 to the 8th. You want to put all those zeros, go ahead. That's less ink for me. It's up to you, but that's the way I would write it, typically. Would that be a big number? Should it be a big number? Yes, guys, that should be a big number. Cars are hard to push. It takes a lot of energy. 1 gallon of gasoline has a tremendous amount of energy in it. So that would be a lot of energy. Now then, I want you to go back in your notes, gather up all your notes that you have. And I want you to look back in this packet of notes and find any problems that are in here that either we did not do or that you have not had time to ask me about. Looks like there's about 5 or 6 problems, I think, that we don't have, and it depends on the class. I'm not sure how many we did do in this class, but it should be close to that. So what questions do you have?
Will the energy stuff that we just learned, will that be on your?
Yes. All of this packet. This is the end of test 1 material. All of this will be on the exam. And I think there were probably 6, maybe 8 questions, maybe not even that many, on sapling that you should have left to do that you can finish today with this. And I may be wrong. There may be fewer than that actually dealt with energy. Yes, ma'am? You will have symbols and elements. You will have symbols and elements on your test. Nothing will be hand graded, but you will have symbols and elements on your test. Yes.
Okay, there was a question that I got to on sapling that like seemed like it would have been like a whatever it's called, like a fusion energy problem, but it didn't give the fusion energy, and I think I figured it out because it was like the specific heat of water.
It may have given it to you. Did it give you the specific heat of water, or did it give you a... Did you look at a hint? Somewhere, something in there should be there. All the materials should be there for the question, and they will be on the exam. There shouldn't be any specific heat unless it's just a general conversion problem, and that's in there, because I haven't taught specific heat to this class. Similar, but not exactly. There was another question over here, I thought? Yes. Wait, which one now?
Oh, it's on the day 2 notes. And it's a question about density.
Blood. Okay. Tell me what you have as the given.
8.5 pounds.
All right, so 8.5 pounds. Keep going. So what goes on top? And then what?
1 pound.
Okay, good.
And then I tried to use the density conversion.
Okay, so what did you put on top?
I put 1 million.
Good. What goes on bottom?
1.06 pounds.
Good. All right. You want to be in what unit at the end? You're in volume now, so what unit do you want to be in volume in the end? All right. You've done this problem basically just a few minutes ago. So what are we going to take milliliters to? Look at the problem you just did. Look at the last problem you did today. But look at it. There's something similar. The very beginning of the problem, it's very similar. Yeah. So then what do you do after quartz? What's the question asking for? That's it. You got it. You got it. What else? What else? Other questions? Anything else? Where is your exam? 11:08. Okay. All right, then. I will see you on Thursday.